areas where there are systematic computations, disciplined computations such as matrix multiplication and convolution. So this is the architecture, the generic architecture of CPUs and GPUs, where every ALU needs to fetch the data from registers. But here, once you fetch the data, multiple ALUs can use it. So systolic array chains multiple ALUs together, so that for every register read you do, you are doing many more computations. Data moves locally between adjacent Ps. So P is same as ALU or sometimes called MAC unit. So which is a register to register movement. Actually, if this ALU can also have a register, then it is just from one ALU, it will have some buffer. It is just movement from here to here. Now, what are the limitations? So systolic array is inflexible. It is limited to a couple of operations. That means it is not a generic computing architecture like CPU, but what a CPU can do. Okay, it takes the same time to load a fully occupied tile as a partially occupied tile. So what does it mean? So suppose here we have this 256 cross 256, right? If you remember from yesterday, the MAC array dimensions were 256 cross 256. Okay, so now if you're multiplying matrices of size 256 cross 256, fine. But even if your matrices are less than 256 cross 256, or if you have sparse matrices, even then your latency will come out to be same. So that's why if the matrix dimension is not a multiple of systolic array dimension, suppose you have suppose you have dimensions of suppose 296 cross 296. Now the systolic array dimension is 256 cross 256. So you will have how much? 40 cross 40 left, which you have to do second time. That 40 cross 40 will have very poor hardware utilization because your MAC unit is 256 cross 256, but you are doing multiplication of just 40 cross 40. This also base bandwidth. Now, TPU does not provide any advantage for sparse matrix multiplication, as I already discussed. That means even if many entries of your matrices are 0, you still have to, do all the computation. Some of the computations are useless, but still you have to do those computations. So of course, some researchers have proposed some optimizations, but those are separate. But as of now, what we are discussing the baseline TPU architecture, it does not avoid those computations. So another thing is TPU does not directly support convolutions. A convolution has to be transformed into matrix multiplication, and then you can run it on TPU. Okay. Whereas there are other accelerators which directly support convolutions. But at least TPU, see, TPU is using systolic array. Systolic array is doing matrix multiplication. Fine. So that's why TPU is not directly doing convolution. It is doing matrix multiplication, and a convolution can be cast into matrix multiplication. So what are the reasons behind efficacy of TPU? So now TPU has a very large 2D matrix multiplication unit, as we have already shown in this slide. This slide, yeah. This is we are doing directly matrix multiplication, whereas GPU they are doing vector-wise vector, right? They're multiplying vectors, and CPUs, at least the conventional CPU, they are multiplying scalar. Okay, while CPU and GPU have smaller 1D multiply units. So matrix multiplies benefit from 2D hardware. Now 8-bit integer support in TPUs improves efficiency over 32-bit floating point numbers. So here you can see compared to 16-bit floating point, and if you are working on 8-bit integers, it gives you 6 times better. If you're doing multiplication, it is 6 times better energy, 6 times better area. And especially if you're doing addition, then it is 13 times better energy, 38 times better area. There's a huge advantage. So 2D organization enables systolic array, which reduces excesses in energy. So just for doing matrix multiplication, systolic arrays are very good. Okay. Now, TPU drops those features which are required by CPUs and GPUs that DNS do not use. So, as I said, CPUs are very, very complex. Like they have caches, branch predictors, Here, caches refer to hardware managed cache, branch predictors, out of order execution, multiprocessing, context switching, and so on. CPUs have traditionally used it, but they add very minimally. They do very little contribution to the performance. Whereas CPU does throwaways all of them. It just begins with a very, very simple architecture. Okay, so this makes CPU cheaper, saves energy, and allows transistors to be repurposed for domain-specific optimization. That means instead of using your transistor to design a branch predictor, you can use those transistors to design a multiplier or ALU. Okay, so because of this domain-specific nature, you can do more specific optimizations. Okay, now TPU has just one program thread, whereas this GPU has 13. You see, this CPU has 18. So this is not for every CPU. Actually, as I will show here, they have taken certain CPUs. So that's what they are comparing here. So that when I say this CPU, it is this CPU, Haswell CPU. So a single thread makes it easier to stay within a fixed latency limit that the neural network applications demand. So see, because you have only one thread, you are not switching between thread, right? From one thread to another thread to another thread. Just a single thread will work. So it allows you to focus on the latency, right? If you remember, CPUs are latency oriented and GPUs are throughput oriented. So even CPUs are latency oriented, but still they have many threads. But TPU is really latency oriented in this sense that it has just one thread. Although TPU also focuses on throughput because it uses very high batch size. And TPU uses dedicated memory. By dedicated, we mean explicitly managed or software managed. So we saw total of, yesterday I asked question to one of the students. We had total of 28 megabyte, out of which 4 megabyte is for accumulator buffer and 24 megabyte is for activation buffer. So TPU invests resources in arithmetic unit and dedicated memories. So it has, compared to CPU, it has only 60% memory. That means almost half the memory, but 250 times more arithmetic units. See, this is a very, very important point because see, although CPUs have caches, but caches are not doing actual computation. Caches are just hiding the latency. Whereas arithmetic units, they are doing actual computation. So it is better to invest in arithmetic units so that you can do more computations. Right? What is the point of simply investing in, caches which are just hiding latency? That's not much use. So now let us discuss evaluation of TPU. So here they have taken one CPU, one GPU. Here this is the area of the die. So TPU version 1 has very less area. Now this is the feature size in which each of these are designed. So here it is designed 28 nanometer. Here the frequency, it has 2300 megahertz, that means 2.3 gigahertz, whereas here it is much lower. Now here TDP is the thermal design power. That is the maximum power this chip will draw. That is very small for TPU. And this is the actual power measurement. Okay. So although the TDP is very high, but actual power will be much less. This is the TOPS, how many operations per second it can perform. So here you can see it's a huge number, 92. Whereas here it is just 2.6 and 1.3. So here this particular GPU that they have taken, it doesn't have separate optimization for 8-bit integers. Whereas now tensor cores, right? So here they have not chosen a GPU which uses tensor core, but there are Volta and Turing which can do optimizations for 8-bit integers also using their tensor cores. Now this is the memory bandwidth. So here it has high memory bandwidth because it uses GDDR. Okay, just today I discussed, right? GPU uses graphics double data rate, GDDR. That's why it has higher bandwidth. And CPU and TPU, they use DDR, either 3 or 4. So because it uses DDR memory, it has low bandwidth. Fine. Now this is the total amount of on-chip memory they have. So this 28 megabytes we already explained. This 8 megabyte is there for the GPU, and this is for the CPU. So here this 51 megabyte, how it comes? It comes by taking together the capacity of L1 cache, L2 cache, and L3 cache. All of their capacity put together is the capacity of on-chip memory of CPU. Now this is the server. So one server can have more than one die. So this is the total things. Okay, total specifications of the whole server. One server can have more than one die. These are the benchmarks. So they have taken 6 benchmarks. So please carefully note the characteristic of these benchmarks, and then we stop. So they have 2 MLPs. Okay, MLP is multi-layer perceptron. LSTM is long short-term memory. And CNN, I'm sure you have heard of the term CNN from me or something else. These are the lines of code in TensorFlow. This is the number of layers they have. MLP only have FC layers. LSTM have few FC layers, few vector layers. And CNNs have many convolution layers. These are the non-linear function. That's not so important. This part is important. Okay, how many weights they have. So CNN1 is very heavy. It has a lot of weights. And this is the ops by weight. What is this metric? What is the other name for this metric? Anybody remembers? What is other name for this metric? Ops divided by weight byte.
Sir, arithmetic intensity.
Yes, that's correct. This is arithmetic intensity. Yeah. How many operations you perform on each byte of weight that you fetch from the memory. And you can see this is very high for CNNs, and this is very low for the LSTMs. So LSTM, it falls in the category of recurrent neural networks, and recurrent neural networks don't have high parallelism. That's why their hardware acceleration is very difficult. Whereas CNNs, they have a lot of parallelism. They have different degrees of parallelism. That's why you can, so as you can expect, which one of these, just by seeing this arithmetic intensity, although actual numbers will show later, probably on Thursday, but just by seeing these numbers, which application will get highest throughput? Please tell me. Just by seeing the arithmetic intensity values. We have discussed a lot of solid examples on arithmetic intensity.
CNN 0.
Yeah, CNNs. Yeah, see, these 2 CNNs will get the highest performance, and this will get the lowest performance. LSTMs. Right? Why? Because they have, although their number of weights they have is not very high, but it's just that they don't have a lot of computations to perform on those weights. Okay. Now, this is the batch size they use. We have already explained what is batching. So first thing you can notice here, batch size is not 1. Batch size is more than 1. This point you please note down. We will show other accelerators where they are specifically optimized for the batch size of 1. But TPU is not particularly optimized for batch size of 1. This is very important. Okay, what is the effect of it? I will explain when I come to the Brainwave accelerator from Brainwave design from Microsoft. But for now, just observe that batch size is not 1. Batch size is between 8 to 200. Okay, and this they are showing that at least in 2016, 16% of their TPUs were running MLP, and 29% of their TPUs were running LSTMs, and 5% of their TPUs were running CNNs. That means at least in 2016, CNNs were not so prominent. MLPs were much more prominent, and this concentration can change later on. So